The next presentation is about deploying the applications on HPC systems in LRZ from David Brayford.
Okay, thanks. My name is David Brayford, and I am a scientist at the Leibniz Supercomputing Center just outside of Munich in a place called Garching. And today I want to just talk about what we've been doing for the last couple of years using containers for different types of applications and workflows. So the motivation for using containers is we want to allow users from non-traditional HPC backgrounds, so for example, the AI people, bioinformatics, to transition their workflows from their development environments, which are normally laptops, to a supercomputer with minimal effort. And it just needs to work. So one of the problems you may already think about is like if you're normally working on a supercomputer, you develop your code on your laptop and you just compile it and run it. But the AI people are actually doing their entire workflow. So it's slightly different than the sort of traditional method of development for software for supercomputing. So not only do the users want to move from their laptop or development environment to a supercomputer, they actually want to run it between different supercomputers. And obviously, as we're moving towards the sort of exascale era of supercomputing, then a lot of the actual hardware is going to be heterogeneous. So it doesn't necessarily mean that what you've built for one system is going to work on another system. So what I put down is it does increase productivity, but it doesn't actually allow portability, because if you're moving from a CPU-only system to a heavily dominant GPU system, you've got to make changes, right? That container is not going to work for you. So it's something to be aware of when you're moving, that you have the flexibility to easily transition your CPU workflows to your GPU workflows, or to some other third party or different accelerator. So some of the key challenges. So you think of the instruction set architecture and hardware. So GPUs, CPUs. So for example, CPUs, you've got the traditional x86, but you now have the ARM systems, and in the future you're probably going to get the RISC-V systems. You've got GPUs traditionally from NVIDIA, AMD, and now Intel are coming up with GPUs. You're also going to have third-party accelerators such as FPGAs. You're going to have different memory setups and different interconnects. So all these things are going to impact either getting your code to actually run or getting performance out of there. Also, the software system. So, for example, the drivers for the GPUs or accelerators, and the MPI. So, as you've seen in the previous talks, that MPI has been a bit of an issue, and it is and the HPC and the HPC community are well aware of this and are working on trying to make it a little bit easier to get MPI. But what the general view is you're going to have your MPI which matches your system MPI, because it's been optimized. Again, for performance and stability, I will again talk about the MPI, is that if you are using the system MPI at runtime, then it's been optimized for performance and stability on that particular system. And that actually is a really important factor when you're scaling to these very, very large number of nodes or cores. Also, it allows you to take advantage of licensed software on the system. So if you're using the software which is already installed on the system, things like MATLAB, things like Gaussian, things like ANSYS, you may not have a license to it, but you're actually using the software which is on the system from inside your container. Again, you'll have a problem in terms of container size. If you look at sort of the AI community where they want to do training, they could easily have a terabyte of data. So not only is that difficult to actually build a container of a terabyte size on a laptop because of the restrictions on your laptop size, but moving that data to a supercomputer is going to be hard. So you're basically moving it via SCP. That could take a long time. So, and also you might actually have the data already sitting on the HPC system, and you don't have to then copy it backwards and forwards. Another issue is IO patterns and execution patterns for the file system. So if you're looking at the HPC systems, you're normally running on a network file system, and they have certain different characteristics than compared to what you normally experience and have, and features you have on a desktop or a laptop. For example, writing lots of small files, not having access to local disks. So the machine at, or the SuperMUC machine at the LRZ and the Linux cluster machines are diskless. So everything's run in memory. So you're writing everything via the spectrum scale GPFS. So the mechanism we use is we actually use Charlie Cloud, and the reason for that is that the system administrators at LRZ gave us that option. They said it was either going to be Charlie Cloud or Shifter. They would not allow Singularity because of the policies of the system admins, which hasn't changed. So if you're thinking about running your containers at LRZ, you have to use Charlie Cloud. So be aware of that. So one of the things we recommend is when you actually build your containers, create a Docker image, because that's basically a recipe of what you're doing. And also, I can't think of any HPC container technology which doesn't have a mechanism of converting a Docker image into their proprietary formats or proprietary image standards. So you can convert from Docker to Charlie Cloud, Docker to Singularity, Docker to Shifter, Docker to Saros, etc., etc. So that does help, because there isn't going to be an easy way of converting from Singularity to Docker. So that's a problem. Also, try to do as much work as you can on your local system, because copying stuff across to the supercomputer is difficult. And if, for example, LRZ might be unique for here, for this workflows, is because we don't have direct access to the internet. So if you want to log in to the SuperMUC machine at LRZ, you have no access to the internet. So you basically having to SCP through a gateway. So having your data, trying to pull it down from the internet isn't going to work. You're going to have to pull it down to a local machine or to a machine which you have access to, and then copy it over to the machine LRZ. Also, we have the the Charlie Cloud in the module system. So you basically, to want to run it, you can just type module load Charlie Cloud, it runs up. Also, one of the advantages of Charlie Cloud is because it's run entirely in user space, if it isn't on the system, you could actually build it locally by using just the commands configure -- prefix, and then whatever you want to install it locally on your system for the user. And it's about just under 5,000 lines of code, so it's pretty quick to actually build. So that's easy. Also, we're able to execute via Slurm. So obviously, if you're thinking of a large production HPC system where we just have users, we're not a research lab where we're running the codes. We are providing a service for external researchers throughout Germany and in Europe and even the world to run on the systems at LRZ. So we want everybody to execute using the Slurm batch system. So this is an example of what we wanted to look at as AI systems, and this was a paper we had published in 2019, but I think it was 2020, early part. And one of the things, if you can see, is what we did is we have this called chrun, and this is the command in Charlie Cloud to actually run your container. The -b is basically a bind command to allow you to mount the directories from the host system into the container. So we have a directory on the SuperMUC NG called /DSS. We have an equivalent directory inside the container called /DSS, and that's the command to actually bind it. So now when you actually run that and you type ls and you can go into that directory, you're actually looking at the directory actually on the host system. The -w is because we're running on a network file system. Then just the container name, then it's -- Python, the name of the script you want to run. And this is actually an example of an MPI job. And we actually, as you can see, we start off running on sort of 4 nodes and we got to 768 nodes. And The workflow, it also involves that we're running 4 MPI tasks, or 4 MPI ranks per node and 12 OpenMP threads per MPI rank. So you can see if the numbers are going down here, you're getting pretty good scaling efficiency. So you're looking at going from almost 95% to just under 90% scaling efficiency at a full island. So that's quite a lot of nodes. If you multiply the numbers by 48, that gives you the number of CPU cores you're running on. And you can see the training time per epoch was just under 4 seconds. What we also did is we wanted to look at the performance in terms of flops. And as you can see, we're getting, at the very high end, we're getting over 2 petaflops of performance. For full disclosure, I'm only measuring the matrix multiply of the very small matrices. So that's why you're getting very, very good performance results out of this. If you look at different areas of the running code and the different application times, you're going to get wildly different mileage than what you're getting here. But we wanted to show the best possible results we could get. This is another example, and this was done by a researcher from LMU in Munich, who's now moved to LRZ. And they wanted to actually run some code which was like a framework for commercial and non-commercial entities. And so one of the issues they had is the containerization crashed due to MPI issues. So this is something which a lot of people experienced. We resolved this by setting the libfabric parameters inside the container. Then we found out, okay, we got it running, but the performance wasn't very good, and we realized it was actually running over the TCP. So it was defaulting to the TCP network rather than going over the high-speed interconnects, which in LRZ's case for SuperMUC was the OmniPath. And we resolved this by installing the OmniPath software, and then it started to run over the PMS2 connection protocols, and the outcome is that suddenly got a big improvement in stability performance, and the applications are scaled like over 100 nodes on SuperMUC NG with over 8,000 MPI tasks. If you type in easy, there's probably a paper. There is a paper somewhere on the internet, and it's probably easy to get it through Google to read more details about what's actually happened. So the second application was software fuzzing, which is slightly different than the previous example where we're looking at scaling on a HPC system using MPI. This certainly had a problem because they wanted to test software on the HPC systems, but only on a single node. But the problem was that the IO patterns crashed the parallel file system. So one of the things a parallel file system doesn't like is to open a lot of very small, open and close a lot of very small files very, very quickly. They're optimized and designed to work with large files using parallel IO. And this wasn't the case, and the work pattern or the workflow was involved creating 6 million very, very small files. This actually crashed the system, and it was pretty problematic. So we switched to mounting, for the example we showed earlier with the -B command. And instead of running it from inside the home, we started running from work and scratch, but that really didn't help. So then contacted the user and said, how much data do you have? And they said, well, they're really tiny files, and we only have a few gigabytes of data. So we decided to let them mount, instead of just mounting the file system, you could actually mount the RAM disk. So instead of writing the data to the files, we're actually writing to the actual memory on the node. This actually worked very, very well, and the users were able to take advantage of RAM disk and to run their applications, and did no longer crash the system, because at the point where we were at this at time is that we were going to say to the users, actually, you cannot run on the system because you're crashing the system, and we are a service system, and we can't be down. We can't have the machine down for a day well, we're having to bring everything back up because your application crashed because we have hundreds of users. So that worked out pretty well for everybody and sort of fixed everything. So it gives like another sort of string to our bow, so we can actually do lots of more different things. So another example, which was relatively recently, is we wanted to use Julia. And one of the issues we found out was what Julia basically installs the packages in your basically home directory. And by default, Charlie Cloud maps the host's home directory inside the container. So one of the things which is problematic, and we had other users who had installed their software inside that container inside /home. So when they actually looked in the container normally by just doing ls into it, they could see their files and their data. But as soon as they started the container runtime, that disappeared because it mapped the actual host's home, so they could only see the host's data. So we recommend that when people are running LRZ, install the applications in a different directory. For example, /my data or /my applications, and then you can access it that way. One of the things we also realized was that the default behavior of Charlie Cloud is also to set the environment to be the same as the host system, which is problematic for things like Julia because it has its internal environments you want to set. So we resolve that by modifying a file and pointing that with the option --set -env to this particular file, which had the information you wanted from the host system. So, for example, things like MPI, maybe other applications, but also the information where the Julia was contained, and that basically worked well too. So one of the things, if you looked at like the point 2, is we started to use Liquid to profile the performance of the application running inside the container from Liquid, which is run on the host system. So again, we mounted we put the environment details of Liquid from the module system inside the environment file, and then we linked that to it. And obviously, then we submitted it in a Slurm script, and it worked. And the outcome is we could actually take advantage of the software installed on the system, because obviously, if you're inside the container, you don't necessarily have access to the hardware directly. So that can be a problem. And that's also going to be a problem when you're looking at sort of things like GPUs, which we don't have on the big HPC systems at LRZ, but on some of the AI systems and smaller systems, we do have GPUs. And at some point, we'll be using for normal HPC users, we'll be using containers for that. For the AI stuff and the AI group at LRZ, they're actually using containers to run the AI software on their systems, but they're basically generally an NVIDIA DGX system. So that's designed to run containerized software from NVIDIA. So you get their stuff from there. So this is some of the examples of the execution this was on a test Fujitsu system. And as you can see, that the compile times and execution times are pretty similar. This information is only recorded inside Julia, not inside Liquid. So this is the actual runtime they're getting, and as you can see, that the difference between the host and the container application is pretty close. So here is the example using Liquid, and if you can see the command we sort of run to get things working. It's not the full command because we have the chrun and all that stuff. Obviously, it sort of makes it a lot bigger in terms of like trying to fit it all in, but it sort of works. And if you sort of go down and look at sort of like the memory read operations, you can see that inside the container, you get much better memory bandwidth. But if you look at the operational intensity, there's much slower inside the container than on the host system. We need to do additional investigation to that. But what we think the problem is that because Julia is a gets compiled on the fly. If you're on the host system for the Fujitsu, you're taking advantage of the Fujitsu compiler. But when we did it inside the actual container itself, we're only using GCC. So there's a big difference in terms of what compiler you're using in terms of performance. So basically, some of the takeaways, we want to start with the Docker file because it gives you a recipe so you know what you've installed. And also, if you move to a different HPC center and you have to change your MPI implementation, for example, LRZ, we use Intel MPI, which is MPICH compliant. You need to use that. You can't use OpenMPI because it is not compatible with MPICH. Again, if you move to a HPE Cray system, their Cray MPI is also going to be different. So those things you want to change. If you're moving from a CPU only system to a GPU only system or GPU heavy system, then you might have to also want to put in the additional, not just the connection to actually communicate between the container and the host for the GPU, but also taking advantage of the GPU algorithms from like CUDA or HIP. Do as much work on your local system. Again, this is a problem for HPC systems is that you don't generally have root on the system. So anything where you're having to build it with root, you can't do that. So do it on your local system. And specifically to LRZ, because we don't have a internet connection, you can't just pull it down from a register. So it's not necessarily straightforward to actually do that. The fourth bullet point is a little bit controversial. So I recommend users to use software already installed on the HPC system if possible, because that allows you to take advantage of optimized software, which may be, for example, MPI, but also, software which is heavily licensed, could be very expensive, and the HPC data center has a license for that software, but you don't. So you can basically map it inside your container and use it, but the container actually doesn't contain the software. So legally and license-wise, you don't have the license. It still doesn't actually move from the data center. However, there is a potential issue if the operating system you're running, the version of Linux, the Linux kernel is different than the one running on the host, and glibc are different. You might start to encounter problems where you get glibc mismatches, but you're using libraries from inside the container and outside the container. So that can be a problem. It's just to be aware of. We haven't experienced that yet, but I think some people have on different systems. And that'll depend on your which operating system you're using, how old it is, and how different it is from the one on the HPC system. It's relatively easy to deploy the software on different HPC systems. So getting the stuff from the Intel x86 system, which was on SuperMUC, which was the first example of the AI. The stuff with Julia we ran on both the SuperMUC NG initially, and then we moved it and rebuilt the container for the ARM systems, so the Thunder X2 and also the A64FX, and it basically took like maybe between half an hour to 45 minutes. So you could do that over lunch, and it basically ran straight away once you got it up and running. Again, mentioned build images for each system, because as I mentioned at the beginning, is that if you're working in high performance computing, the second word is performance. So if you have something which will run everywhere, it's not going to run well everywhere. So you actually want to take advantage of the system. And also the HPC centers want you to, for example, take advantage of the high-speed interconnects. If you're using, for example, Mellanox systems for interconnects, they actually do some processing, like numerical processing inside the network fabric. So for example, it does reduction operations inside the network fabric. So you could take advantage of that if you're doing things like a lot of matrix operations where you need to do a reduction operation. You could take advantage of that and get better performance. Again, use host software inside the container. It's relatively easy. You just use that bind command. In terms of performance, there's no big difference. A year or so ago, there was a paper written by some of the guys at Sandia, Livermore, Los Alamos, on the performance of containerized software versus bare metal software on HPC systems, and they didn't, the difference was like minimal. And the experience we've had at LRZ is the performance differences are minimal. Generally, if there is a performance difference, it's generally to do with, for example, your MPI is not configured correctly inside if you're scaling out, or you're using a different compiler. So you're using an optimizing compiler on when in one form and inside or outside the container, and the opposite, you're using a different compiler which is generating a different performance code. So those are things we've actually seen. In terms of the security, LRZ, we have quite strict security, so we are using Charlie Cloud for that reason. And there's a paper at Supercomputing this year, and it should be either on the archive called, I think it's Minimizing Privileges and HPC, or Building HPC Containers, or something like that. The authors are Shane Cannon, Reed Pedrowski, and Andrew Young, and Tim Randalls. So those might be interested if people are interested in the security side of that. So documentation. So the webpage at LRZ has information on how to run Charlie Cloud, how to build your applications on the system. A GitHub repository from the Julia staff if you're interested in the quantum side of stuff and seeing how that works. We have various different publications. So we have the initial test where we publish, getting the AI frameworks running on a secure HPC system. The follow-up to that paper was, getting it running at petascale. And then at Supercomputing the Canopy Workshop, HPC Canopy Workshop this year, we published a paper on how to deploy the containerized Quantex quantum simulation on different HPC systems at LRZ. My contact details is my LinkedIn account and also my Twitter.
Thank you very much.